Welcome to the KEQ family. In this video, we're going to be looking at all these different constants very quickly, but we're going to focus on the reaction quotient, QC. Up until now, we've been talking about KEQ and how it refers to the equilibrium constant. We've talked about how to write those equilibrium expressions and even how to use them with some basic calculations. In the previous video, we talked about Kc, the equilibrium constant in regards to concentration. And in this video, like I said, we're going to be talking about QC, the reaction quotient. It's important to note that the reaction quotient is just a calculation of a current ratio. So we're not at equilibrium yet. We're either on our way towards equilibrium, or the system's been stressed and trying to return to equilibrium. If our QC and Kc values are equal, so this is that middle scenario, there's no shifting required. That means we are at equilibrium currently. However, if QC is greater than Kc, so over here on the right, we have way more products than reactants. So we are above our Kc value, our equilibrium. To return to an equilibrium value of Kc, we have to decompose our products in the reversible reaction and make more reactants. If you look at this mathematically, that means our numerator of our ratio is much higher than our denominator, and to bring that value down, we have to make our numerator smaller and our denominator bigger. If we make our denominator bigger, that's the equivalent of making more reactants, because remember, the reactants are in the denominator. If we jump over to the left-hand side, the scenario that has the QC bar lower than the Kc bar, the only way we can reach equilibrium is by raising that QC value. We can raise the QC value by making more products and lowering our concentration of reactants. This time it's the reverse. So what's important to note here is that if QC is less than Kc, we need to make more products to reach equilibrium. And if QC is greater than Kc, we have to make more reactants to get to equilibrium. So this is our forward and reverse reactions. All right, time to apply that new knowledge. I have 3 questions here. I'd recommend maybe pausing the video at the start of each question and trying it yourself. It'll help you if you try it first and then watch the answer and then compare my answer to yours. That self-correction piece, very important. So go ahead, pause the video now, and then when we return, we'll get started. All right, hopefully you actually pause the video and it's not me just having this awkward cut. So like I said, we're going to start by answering this question. I have a QC expression already. Remember, QC is the reaction quotient. So let's go ahead and fill in these values. Well, CO2 is 10, H2 is 12. We're just going to go through really quickly and fill these out. CO is 1.0 and H2O is 1.5. So when you do the quick math, you're going to get a numerator of 120 and a denominator of 1.5. It's important to note, remember that the products are on the top. Okay, so the products are on the top and our reactants are on the bottom. We can already see that products greatly outweigh the reactants. So when we calculate our QC value for this, we're going to get a value of 80, which is really quite high. Remember that when QC and Kc are 1, we're at equilibrium. So this is equilibrium right here. I'll note it with a little e. Our value of 80, however, is much higher than 1. Our QC is way over here. So that tells us that our QC is higher than our Kc. So the only way to lower this bar to reach the height of Kc is to consume some of these products and make more reactants. So we need to use our reverse equation. So when it says calculate the QC for the above concentrations, we've done that. It's 80. And then when we say compare your QC to the given Kc, well, we can use this number line. Our QC is much higher than Kc. We have to bring QC down. Remember, 1 is equilibrium. And by bringing QC down, we're using our reverse reaction. We're going to make more reactants. Okay, so we're using our reverse reaction, which is very important. I'll highlight it up here in the reaction itself. So let's move on to question number 2. Again, pause the video, try it out with what you know, what you just learned in that last question, and then return back and see how you've done. All right, hopefully you actually tried question number 2. Remember, apply your knowledge as you're learning. Pause the video, try it out, compare our notes, and that self-correction will help you understand all of this. Again, QC value is already given to us, or sorry, the QC expression. We need to calculate the QC for the above concentrations, so let's go ahead and fill in our values. We're going to have 2 multiplied by 5. I'm just getting these from the data table up here, and 9 and 7. So let's put these in brackets, put a line there. All right, well, 2 times 5, that's 10, and 9 times 7 is 63. 10 over 63, we can already see that's going to give a decimal value of 0.158. That's quite low. Okay, so remember, when Kc and Qc are equivalent, that is a 1-to-1 ratio, and that is what we call equilibrium. Okay, so equilibrium is right here on the number line, but we are at 0.158. That's closer to 0, so we're somewhere down in this range over here. Okay, so here's our current QC, and we need to bring it up to reach equilibrium. So that's going to be our forward reaction. I'll note it up here on the reaction again. So that's going to be our forward reaction to reach Kc. What that means is we have a QC value which is lower than Kc. So we have to bring it up, and by bringing it up, we're using our forward reaction. What that means is our denominator needs to go down, and our numerator needs to go up to have this ratio come out closer to 1. Okay, so that's a mathematical proportion. We lower the denominator and raise the numerator, and that'll raise this value closer to 1. So go ahead, pause the video before we start question 3. This one will be really quick, and then we'll self-check. Again, I can't stress this enough. I really hope you paused that video there when I requested you to do so. You need to practice these questions yourself as well. So let's use this data table, and let's do question A. Calculate the QC for the above concentrations. CO2 is 1.0, H2 is 5.0, and then we're going to be over 5.0 and 1.0. I can already see a pattern here. So we have 5.0 on the top and 5.0 on the bottom, and that's going to equate to a value of 1. That tells us that our two values are equal. Our QC and Kc are equal because Kc is right up here. Okay, so at 1, we're going to be at equilibrium, and our QC is also at 1, so let's put KEQ here, and we'll put QC already here, and you'll notice they're at the same line. So we are at equilibrium. There is no shift in this question. Okay, we don't have to use the forward or reverse reactions. Hope this video helps you understand what we call QC, the reaction quotient, and how it is compared to Kc or KEQ. And in the future, please let me know if you have more questions.